Hi, today we will see the chapters on numbers, rectangular coordinate system, quadratics and polynomials. These are all the chapters we will be seeing today. There are 15 chapters under numbers, under Cartesian system 13 chapters, and quadratics 8 chapters, and under polynomials 13 chapters. We will see first number system chapter 1. Fundamental theorem of arithmetic. Prime factorization of a natural number is unique except for the order of its factors. That means any natural number can be factorized as prime numbers. 100 is equal to 5 into 5 into 2 into 2. All are 5 prime numbers. 5 and 2 are prime numbers. Only thing is the order of factors is 5 occurs 2 times, 2 occurs 2 times. So, prime factorization of any natural number is unique except for the order of its factors. 5 squared, 2 squared are divisors of 10 squared. Therefore, 5 and 2 are divisors of 10. This is an important property of prime number because 5 squared and 2 squared are divisors of 10 squared. That means since 5 and 2 are prime numbers, 5 and 2 are divisors of 10. Natural number is a positive integer. Unique number is a positive integer with no repeating digits. All digits ought to be different. 21 is unique, 33 is not because it is repeated. Golden ratio is 1.618. That is the ratio of longest length to shortest length. L plus S divided by L. So, real number, natural number, whole number, integers, rational numbers, irrational numbers and complex numbers. These can be represented as unique sets. Now here is a real number line starting from 0 towards right positive integers, towards left negative integers. And this is a golden ratio. A is a long L, B is S. So L plus S divided by L is 1.618. Natural numbers and their operations, we will continue with the operations, addition, subtraction, multiplication and division. Closure property. What do you mean by closure property? If any operation is conducted on elements within a set, then it gives a result which is within the same set. That means if you take integers, these operations should result in integers. Likewise, if that is satisfied, it is called closure property is there. Otherwise, it is an open property. Integers are closed under addition. Integers are not fractional. Fractions are different. That is, it can be represented as a ratio of two integers. And numerator will be less than the denominator. Natural number is 1, 2, 3. This is a list form. Whole number 0 is included and 1, 2, 3 are added. 1, 2, 3 comma I should put. Therefore, it goes on. Z is equal to y is such that y is equal to plus or minus x, where x is an element of whole number. This is set builder form. The set Z is defined in set builder form here. Here I have represented as a list here. Only 1, 2, 3 is included. If I want to add all other numbers, then I can put a comma and put 3 dots. Here, rational number is defined. X is such that x is equal to p by q, where p and q are elements of integers and q is not equal to 0 because divisor should not be 0. And irrational number is all the real numbers which are not fractional. That is, x is such that x is an element of real number except the fractions, except the rational numbers. And real number is defined as x is such that x is an element of R. Now we will go to the second chapter, rational numbers. Number system, we know natural numbers are 1, 2, 3, 4. Whole numbers are 0 is included to the natural number. Integers or negative natural numbers are included. And fractions are p by q, where p and q are elements of whole numbers. That is this set. And q is not equal to 0. And rational numbers are p by q, where p and q are elements of integers because negative numbers are also included and denominator q is not equal to 0. Irrational numbers are defined as root 2, 0.1238 pi and other numbers which cannot be put in the form of rational number. A number that can be written as a fraction where both numerator and denominator are integers and denominator is not equal to 0. That is what we defined as a fraction. A rational number is equal to p by q, where p and q are elements of integers, q is not equal to 0. We have defined umpteen times, I have defined once more, no problem. Introduction. The properties, closure properties, commutative properties, associative properties, distributive properties, and additive inverse and multiplicative inverse. Additive inverse is 0, multiplicative inverse is 1. And rational number on number line we can represent. Rational number between any two numbers on the real number can be represented by the midpoint. Now what is closure property? Operations give results from the same set. If you do operations from a set and the result should be from the same set. Commutative law we will see a plus b is equal to b plus a. The order can be reversed. Similarly ab can be written as ba. You can multiply 1 and 2 or 2 and 1, both gives the same result. That is commutative property. Associative property means two terms can be associated in any order. A plus b plus c plus d, here b plus c is associated, combined, and is equal to a plus b plus, here c and d are combined, plus c plus d. Therefore this is called associative property. And distributive property is a plus b into c plus d is equal to a plus this c and d can be distributed to be bc plus bd. This is distributive property. And the rational number between any two numbers, as I told you, you can use midpoint or average of the two numbers. Now we will go to the third chapter, real and complex numbers. Complex number c is equal to a plus ib, where a and b are real and imaginary parts. Complex number can be written in three forms. We will see all the three forms now. Rectangular form, that is x plus iy, same as a plus ib, and where x is equal to r cos theta, y is equal to r sin theta, theta is called argument, r is called modulus. Polar form, trigonometric, r times cos theta plus I sin theta. You can see that r cos theta is x, r sin theta is y, and r is equal to the modulus root of x squared plus y squared, and theta is argument equal to tan inverse of y by x. So polar form is an Euler form, is r e power I theta, because e power I theta is nothing but cos theta plus I sin theta. This is convenient because multiplication is very easy. E power I theta into e power I theta n times is e power I n theta, which is cos n theta plus I sin n theta. E power I n theta is equal to cos n theta plus I sin n theta. For this reason, this is always convenient for doing problems. Z is equal to x plus iy is a complex number, and you can represent a complex number by its location, taking x along the x coordinate, y along the y coordinate, and fix the point. Modulus of z is the distance and theta is the direction. Z1 is equal to 2 plus I3 is the location of a complex number. That means you take along the x-axis 2 and y-axis 3 and fix the point. Right. Now this is how you fix. You take along the x-axis 2, along the y-axis 3 and fix the point here. Z1 is equal to 2 plus I3 represents, there are four options. The correct answer is, it represents location of the point with respect to the origin. That is, Z is equal to 0. Option A is the correct answer. Z1 is equal to 2 plus I3 represents location of the point A, which we have seen now. Then modulus of Z1 represents, the same options are given. The correct answer is, it gives the distance of the point from the origin. That is, Z is equal to 0. Therefore, the correct answer is option C. Now, Z1 is equal to 2 plus I3 represents the location of the point A. Argument Z1 represents, the same options are given. So, the correct answer is option B, the direction of the point from the origin. So, this is the direction, and theta is the argument. So, option B is the correct answer. Z1 is equal to 2 plus I3. Z2 is equal to 3 plus 4i. These are 2 points. And modulus of Z minus Z1 is equal to modulus of Z2. Modulus of Z2 is the distance, that is the modulus of 3 plus 4i, which is 5. And z minus z1 is nothing but the distance of this point from the z point, locus. So the distance of the locus from a fixed point z1. That means it is the equation of a circle. So the correct option here is, it's a circle with center z1 and radius 5 units. So the correct answer is option A. z1 is equal to 2 plus i3, modulus of z minus z1 is equal to 3, then 5 plus 3i is a point on the circle with center z1 and radius 3 units. See, radius is 3 units is okay. We will see z minus z1 distance, right? 5 plus 3i is a point z. So we will find out the distance between these two, that is 5 minus 2 and 3 minus 3. Therefore it is 3. So square root of 3 squared is 3. Therefore it is a point on the circle with center z1 and radius 3 units. But before ticking this option, we will go to option B also. 2 plus 6i, consider it as a z point. The distance is 2 minus 2 is 0, 6 minus 3 is 3, 3i. So modulus of 3i is 3. Therefore 2 plus 6i is a point on the circle with center z1 and radius 3 units. Both are correct. Therefore option C, both A and B, is the correct answer. Z is equal to x plus iy. We will see conjugate, modulus and argument. Conjugate is written as z bar, that is you change the sign between the real and imaginary part. X minus iy is the conjugate of x plus iy. 2 minus 3i is the conjugate of 2 plus 3i. So modulus is square root of x squared plus y squared. Please note, irrespective of the sign between the two, modulus is same. So the modulus of conjugate and modulus of the number z, both are same. Argument is tan inverse of y by z. That again remains the same for both conjugate and the number z. You will see properties of conjugate. The conjugate of a power is equal to power of the conjugate. Right? And z into conjugate of z is equal to square of the modulus of z. So you can verify these things. Take any number 2 plus 3i and 2 minus 3i, multiply these two, and then take the modulus of 2 plus 3i, square it, and you will get the same answer. So z plus conjugate is equal to 2 times real part of z. Z minus z conjugate is equal to 2 times imaginary part of the z. So you can see here z plus z bar, x plus iy, conjugate is x minus iy. If you add these two, imaginary parts cancels, leaving you 2 times the real part x. Similarly here, if you subtract, then x minus x cancels, real parts cancels, leaving you the imaginary parts. Plus y is plus 2iy. Now we will see a condition. If this is equal to 0, what happens? If this is equal to 0, what happens? Now if z plus z conjugate is 0, then it represents purely an imaginary number. If z minus z bar is equal to 0, then it represents purely a real number. Right? You can see here x plus iy plus x minus iy is equal to 2x is equal to 0. Therefore only y has a value. That means it is purely imaginary. Similarly here, x plus iy minus x minus iy is equal to 2y is equal to 0. Therefore only x has got a value. Therefore it is purely a real number. Now we will see the properties again. Conjugate of a conjugate is the original number. So double conjugate, that is conjugate of a conjugate of number is equal to the number itself. Z double bar is equal to z. And conjugate of a product is equal to product of the conjugates. And this is what is used to find out the relation. Conjugate of z power n is equal to nth power of conjugate. That means order is immaterial. Conjugate of a division is equal to division of the conjugates. Conjugate of a sum is equal to sum of the conjugates. Conjugate of a difference is equal to difference of the conjugates. Z plus Z bar is equal to 2 times real part of Z. Z minus Z bar is equal to 2 times imaginary part of Z. That is what I have written it here. I have taken a number x plus iy as Z and conjugate is x minus iy. If you add, you will get 2 times x, which is 2 times real part. Similarly here, if I subtract, then x and x gets cancelled. You get 2 times imaginary part, 2 times iy. and z into z bar is equal to x squared plus y squared. This is an important relation, and z squared plus z bar squared is equal to 2 times x squared minus y squared. This also will be very useful for your IIT preparation. Now, modulus of z power n is equal to nth power of modulus. Modulus of sum is equal to sum of the moduli, and no, it is not always. Please note here, if the modulus of sum is equal to sum of the moduli, then it indicates the origin and the 2 points z1 and z2 are collinear with origin at one of its ends. Similarly, this also is valid. If the modulus of z1 minus z2 is equal to modulus of z1 minus modulus of z2, then again the origin and the points z1 and z2 are collinear with origin at one of its ends. Right? Because all the 3 points are origin, z1 and z2 are collinear in both the cases, and origin will be one of its ends. Now, modulus of z1 plus z2 is equal to modulus of z1 plus modulus of z2, then origin z1, z2 are collinear with origin at one of its ends. That is what we have seen. We will verify this condition. I will take an example. Z1 is equal to 1 plus I and Z2 is equal to 2 plus 2I. What is Z1 plus Z2? 3 plus 3I. And what is modulus of Z1 plus Z2? Square root of 3 squared plus 3 squared. That is 3 root 2. And modulus of Z1 plus modulus of Z2 is equal to, this is root 2, root of 1 squared plus 1 squared. Again this is root of 2 squared plus 2 squared, that is 2 root 2. So adding you will get 3 root 2. Both are same. You can do it yourself and verify. And origin Z1 and Z2 are collinear. You can mark this at a graph sheet, organ diagram. You will see that all these three are collinear. And modulus of Z1 minus modulus of Z2 is equal to modulus of Z1 minus modulus of Z2. We will verify the condition for the same points. Z2 is equal to 1 plus I, Z1 is equal to 2 plus 2I, and modulus of Z1 minus Z2 is equal to square root of 1 plus 1, that is root 2, and modulus of Z1 minus modulus of Z2 is equal to 2 root 2 minus root 2, that is root 2, and both are same, and you mark the points, all the 3 points will be in a line. More properties we will see. Modulus of Z is equal to 0 means Z is equal to 0. Modulus of a conjugate is equal to modulus of the Z. And modulus of Z1, Z2 is equal to product of the moduli. Modulus of Z1 into modulus of Z2. And this is what we are using to prove that modulus of Z power n is equal to nth power of modulus of Z. And modulus of a division is equal to division of the moduli. And Z into Z conjugate is equal to square of the modulus of Z. Triangle inequalities we will see. Modulus of Z1 plus or minus Z2 always less than or equal to modulus of Z1 plus modulus of Z2. Similarly, modulus of Z1 plus or minus modulus of Z2 is greater than or equal to modulus of Z1 minus modulus of Z2. So it is always less than the sum and greater than the difference. And argument of a product is equal to summation of the arguments plus 2n pi, because it will be repeated, no, after one revolution it comes to the same angle, therefore plus 2n pi, because 2 pi means one rotation, n represents number of rotations. Argument of division is equal to the difference between the arguments. Argument of Z1 by Z2 is equal to argument of Z1, that is numerator, minus argument of Z2, that is denominator, plus 2n pi as usual. Argument of Z power n is equal to n times argument of Z plus 2n pi. It is obtained from the relation 1, because argument of Z squared is argument of Z1 into Z1, that is argument of Z1 plus argument of Z1, that is 2 times argument of Z plus 2n pi. Argument of conjugate is equal to minus argument of Z, because Z conjugate is the mirror reflection on the bottom below xy plane, below x axis. Now we will see representation of complex number in polar and Euler form. So z is equal to x plus iy is a complex number. Polar form is z is equal to r cos theta plus I sin theta. E power I theta is equal to cos theta plus I sin theta. We know that. And Euler form is z is equal to r e power I theta, because modulus of e power I theta is 1. Because cos square theta plus sin square theta is 1. Okay. Modulus means what? Cos square theta plus sin square theta for r is equal to 1 here. If we have modulus of z and argument, write z in Euler's form, because that is more convenient for doing difficult mathematics. Euler's form is very efficient in handling big and bad powers of a complex number. Z squared plus z plus 1 is equal to 0, and z is equal to, you can find out the value of z using quadratic formula, which you will see later, and this we will name as omega and omega squared. Right? One is omega, another is omega squared. So you can take the cube root of 1 as omega or omega squared. And similarly, z squared minus z plus 1 is equal to 0. Z is equal to minus omega or minus omega squared. So roots of z squared plus z plus 1 is equal to 0 or omega and omega squared. Roots of z squared minus z plus 1 is equal to 0 or minus omega and minus omega squared. Very important, these two. Consider z cube is equal to 1. Roots of this equation are called cube roots of unity. And z cube minus 1 is equal to 0. Z minus 1 into z squared plus z plus 1. That is the expansion of this left hand side. Therefore, z is equal to 1 or z equal to minus 1 plus root 3i divided by 2, or z is equal to minus 1 minus root 3i by 2. So 1 is taken as omega and this is taken as omega squared. Right? So 1 into omega squared is, you multiply these two with 1, you will get the 1. Right? So this, if we are doing it, you can find out, multiply these two, you will get this minus 1 by 2 whole squared minus root 3i by 2 whole squared, and that is 1 by 4 plus 3 by 4, that is equal to 1. And then we will see set theory now. All real numbers are a set. X is such that x is an element of real number. You can also write in the list form minus infinity to infinity. X is equal to minus infinity to plus infinity, excluding minus infinity and plus infinity, because we cannot locate infinity, because infinity is undefined. Inequality notation, we will see x is greater than or equal to minus 5 less than 10. How will we give the notation? Set builder form we will give x is such that x is greater than or equal to minus 5 less than 10. We will use the same thing in set builder notation. In the list form, in the interval notation, we will give minus 5 comma 10. Here it is closed bracket, open bracket is closed bracket, and closed bracket is closed bracket. That means this is 10 is not included and minus 5 is included. That is what is meant by this. And x is less than 100. Set builder form is x is such that x is less than 100. Here open bracket minus infinity comma 100 close bracket, both are open ends. X is greater than or equal to 100. That means x is such that x is greater than or equal to 100. Here what we will do is square bracket 100 comma open bracket infinity. Open bracket infinity means infinity is not included. Square bracket 100 means 100 is included, because x is greater than or equal to 100. And x is greater than minus infinity less than infinity is given by x is an element of real number. Here open bracket minus infinity close bracket infinity again. So both are open ends, that is not included. And then we will see construction of subsets and subset operations. Let A and B be two sets. A cross B is a Cartesian product of sets A and B. Number of elements in A cross B is equal to number of elements in A into number of elements in B, where number of elements in A is NA, number of elements in set B is NB. Elements of A cross B are in ordered pairs. Please, here elements are individual numbers. Here it comes in pairs. First from set A and the second number from set B. So subset of A cross B is a set consisting of any number of elements in A cross B. Please go through that, try to understand. I will also show you with example. So if A is equal to 2, 3, B is equal to 3, 5, 7, then A cross B is, it will have 6 elements, because number of elements in A is 2, number of elements in B is 3. So product is 2 into 3, 6. Therefore we will get 6 elements. We will see. We will take first element from the first set and then pair with all the elements in the set B. So 2, 3, 2, 5, 2, 7. Then we will take the second element from the first set 3, and pair with the elements in B, that is 3, 3, 3, 5, 3, 7. Therefore, totally 3 elements are there, and each element is a pair of numbers, ordered pairs we'll say, right? This is what I have explained, and then we will go to the examples. Empty set, that means no element is there. It can be represented by a parenthesis like this and with nothing inside, or 5. Both represents, it's an empty set. You can also represent it by capital letter E. Number of elements in capital E is 0. Even though we say that nothing is there, that is nothing is there, 0, right? So it is in quite in order. Singleton means there is one element there. Please note, empty set is not a singleton. So S is equal to 4 means number of elements in set S is 1. That is only one element, 4 is there. Finite set is, we can count the number of elements. So here number of elements in set F is 5. Infinite set means we cannot count the numbers. N is equal to 1, 2, 3 goes on, all the natural numbers. So number of natural numbers we do not know, so infinity. Equal set means two sets we are comparing. The number of elements will be same, and the elements also will be same. See, E is equal to EARTH, 5 elements are there. H is HEART, here also 5 elements are there. This is equal set. E and H are equal sets. Number of elements are 5 and the elements are EARTH. And equivalent sets is the number of elements are same but the elements will be different. Here EARTH 5 elements are there. Here 1, 2, 3, 4, 5 elements are there. The elements are not equal. Therefore, E and F are equivalent sets. I hope you have understood the equal set and equivalent set differences. Now, universal set means all the elements in our study, contains all the elements of which or other sets or subsets. So, we are going to study from the universal set. All the subsets are coming from universal set. A set of all vowels A, E, I, O, U. This is a universal set. If we are going to study about the vowels, A is equal to A, E, I, B is equal to I, O, U. Please note, we have taken subsets here. Subsets set. A set is a subset of B only if every element in A is also an element in B. That is, A is a subset of B. Please note the symbol equal to sign also is there, because if A and B are equal, then also A is a subset of B. B is SIR. Subsets 2 power n. There will be 2 power n subsets. What is 2 power n? Number of elements is 3. 2 power 3 is 8. We will see 8 subsets from here. One is SIR itself, right? A1. A2 is I take S and I, then S and R, then I and R, then I will take S alone, I alone, R alone, then I will take null set. So totally 8 subsets are there. That is what we have proved. Number of subsets is equal to 2 power n, where n is the number of elements in the original set considered. Proper subset means this SIR should not be included. If at least one element in B is not contained in A, then it is a proper subset. See here, A is equal to 135, B is equal to 1357. So at least one element is not there in A. Therefore, A is a proper subset of B. That equal to sign will be removed here. I hope you have understood this. We will go to the next slide. So, G is equal to HAB I have taken, H is equal to H and B, H is a subset of G. Number of elements in proper subset is equal to 2 power n minus 1, because 2 power n is the total number of subsets in the power set, right? Superset we will see now. A set containing all the elements of another set. A is a superset of B. I will take A is equal to SIR, B is equal to SIR. Then all the elements are contained in A. All the elements in B are contained in A. That's what superset I will put. Proper superset means A5 is equal to S, A6 is equal to R, A7 is equal to I, and A8 is equal to null. And if at least one element in A is not contained in B, that is A is equal to 1357, B is equal to 135, then A is a proper superset of B. That is equal to sign also will not be there. Please, A is a proper superset of B here. Okay. Power set. Power set contains all the subsets of a set, that is n. Number of elements in power set is equal to 2 power n. Therefore, proper subset or proper superset, number of elements is 2 power n minus 1. That is what we have seen in the previous slide. Now we'll see examples of set operations and counting problems. Number of subsets of A is equal to 2 power number of elements in set A. Example we will take, if A is equal to 2, 3, B is equal to 3, 5, 7, then the number of subsets of A cross B is equal to, so the correct answer is 2 power 6, right? Because A is equal, number of elements in A is equal to 2, number of elements in B is equal to 3. So elements in A cross B is equal to 6. So number of elements in A cross B is equal to C. Number of subsets of A cross B, that is what is asked, not number of elements. Number of subsets of A cross B is 2 power number of elements in A cross B, that is 2 power 6. Option C is the correct answer. Now we will see relations. Let us show in a Venn diagram. A and B are shown. Definition: let A and B be two non-empty subsets. Any subset of A cross B is called a relation from A to B. That is the definition of A. Any subset of A cross B is a relation from A to B. A is equal to 1 to 2, B is equal to 3, 4, 5. A cross B is given here. I take any elements 1, 2, 1, 3, 1, 4 or 1, 3, 1, 5 or all the elements, all are called relations. Create any random subset R1, relation 1 from A to B. R1 is equal to, I take only 3 elements at random, 1, 3, 1, 5, 2, 5. It is a relation. A cross B has 6 elements, hence it has 2 power 6 subsets. I got 2 power 6 relations possible. All these subsets are relations. Why do you name it as relations? We will see here. Description of relations. There are 3 ways to describe a relation. R1 is equal to 1, 1, 2, 3, 3, 5. This is by listing, ordered pairs. R2 is by set builder form, x, y, such that y is equal to related to 2x minus 1. X is an element of A and y is an element of B. And then third one, R3 is equal to x related to y implies y is equal to 2x minus 1. X is an element of A and y is an element of B. This is an implied description, right? Okay. Now, if x, y is an element of real number, then we call y as the image of x and x as the pre-image of y. This is an ordered pair where y is the image of x and x is the pre-image of y. Relation from A to A, we call it as relation on A. B also should be A here, right? And the same element should be there. What is the image of 3 and what is the pre-image of 3? Here image of 3 is 6 and pre-image of 3 is 1. Subset of A cross B is a relation from A to B. Subset of A cross A is relation from A to A. Subset of A cross A is also called a relation on A. Right? I have taken here same sets A and A. Now we will see the functions. Let A and B be two non-empty sets. A function from A to B, that is f such that A to B is a relation such that all the elements of A are related to the elements of B and no element of A is related to more than one element of B. That is, no element of A is related to more than one element of B. That is, image is unique. Every element in set A should have a unique image. And then we will see relations examples. Subsets of A cross B, subsets of A cross A. Do you understand this? Empty relation, universal relation, identity relation. We will see all these things. Reflexive relation, symmetric relation, transitive relation, equivalence relation. These are all there. Empty relation is phi. Phi is called empty relation. We can represent like this. Universal relation is let A B be a set and A cross A is a subset of A cross A. And A cross A is a relation on A. A cross A is called universal relation. Let A is equal to 1, 2. Then A cross A is 1, 1, 1, 2, 2, 1, 2, 2. I have taken one element from A and then pairing with the same elements. Identity relation is let A be a set. If every element of A is related to itself, then it is called identity relation. So IA is equal to A comma A, where A is an element of A. That means here I have to take 1 comma 1, 2 comma 2. 1 comma 1 alone is not a identity relation. This is an identity relation. Start. Now we will see relations examples. Subsets of A cross B. Subsets of A cross A. You understand this? I think I am just replacing B by A. An empty relation, universal relation, identity relation, and reflexive relation, symmetric relation, transitive relation, equivalence relation. These are all there. We will see if possible. Now, empty relation. Suppose you take a set A and phi is a subset of A cross A. Then phi is a relation on A, because all subsets is a relation. All subsets of A cross A or A cross B is a relation. Now, phi is called empty relation. Phi can be represented like this. Universal relation. Let A be a set and A cross A is a subset of A cross A. Then A cross A is a relation on A. So A cross A is called universal relation. From the set A, the universal relation is only A cross A. And 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 2. I take elements from the set and pairing with the same elements in set A. Identity relation is if every element of A is related to itself, then it is called identity relation. Like for example, IA is equal to A comma A, where A is an element of A. Is called identity relations. That is 1 comma 1, 2 comma 2. Please note, not 1 comma 2 is not included, and 1 comma 1 alone also is not correct. So it should be 1 comma 1 and 2 comma 2, or both should be included. Then only it is a identity relation. Let A is equal to 2 comma 3. A cross A is equal to 2 comma 2, 2 comma 3, 3 comma 2, 3 comma 3. Relation 1 is null set, called an empty relation. Relation 2 is A cross A, that is 2 comma 2, 2 comma 3, 3 comma 2, 3 comma 3. This is also a relation called universal relation. R3 is 2 comma 2, 3 comma 3, called identity relation. Right? R3, this is not an identity relation. Is not identity. And now we will see function examples. Which of the following is a function? We will see here. We have taken all 4. Now, option 1, option 2, option 3, option 4. A, B, C, D is there. 1 and 2. 1 and 3, 2 and 3, 3 and 4. We will see here 1 first of all. Oh, it is a function, definitely. And then this is not a, this is also a function, 1 and 2. Yeah, option A seems to be correct. Here we will see here, this is not a function. Why this is not a function? Because M3 is not included, and here it has got it does not have a unique image. C2 has got 2 images, M1 and M3. Therefore 4 is not correct, and then 3 is also not correct. Therefore 1 and 2 is the correct answer. This is many to one function, right? 2 is called many to one function. Option A, 1 and 2 is correct answer, right? This is 1 to 1 function. The 2 is called many to one function, because many inputs have got unique output. 4 is not mapped, therefore is not correct. 5 is not uniquely mapped, right? That is the reason I am telling, right? Okay, not 4. C2 is C1, 4 is C1, is not mapped here. Here this is C2 is 5, that is 4, 5, 6 contain, right? C2 is not uniquely mapped. Which of the following relations on the set 4, 5, 6 is not a function on the same set? Why? 4, 5, 6, this 4, 5, 6 is okay, and 4, 5, 6 many to one. Here 4, 5, 6, this is many, 1 to many, it is not a function, this is not a function, and here 6 is not mapped. right? Therefore 1 and 3, this one, you'll see. So 4, 4, 5, 5, 6, 6 is a function, right? 4, 4, 5, 5, 6 is a function. 4, 5, 4, 5, 5, 5, 6, 4. This is also a function. This one 4, 6, 5, 4, 6, 5 also is a function. This is not a function because it's not a function, it is a relation, because 5 has no unique mapping. 5, 4, 5 has got 4 as an output, 5 has got 5, 6 also as a output image. Right? Therefore, option D is the correct answer. Right? 2 reasons. 5 is a friend with this 2 and 6 is alone. Here 6 is alone. That is why this is not a function. F is such that A to B, A related to B, where A is equal to -1, 1, 2 and B is equal to 1, 4, 9, defined by f of x is equal to x squared, is a function for which A is equal to -1, 1, 2 is called domain of F. This is called domain. B is equal to 1, 4, 9 is called codomain of the function. Very good. And C is equal to 1, 4 is called the range of F, which is a collection of all images. Images alone, that is outputs alone, form a set called the range. Right? 1, 4 is a range here. I hope you have understood what is domain, codomain and range. And here is a function. -1 is paired with 1. Image of -1 is 1. Image of 1 is 9. A has no image. Right? 2 has no image. Right? This 2 has no image. Here 1 has 2 images, not a unique image. Right? Therefore, these two are not functions. Right? Both are relations, but neither is a function from A to B. Okay. Now here is a vertical line test, because one x input has got 2 outputs. Therefore, this is not a function. Vertical test. Here again, it has got more than this has got 1 output, another output, 3 outputs. One input has got 3 outputs. Therefore, it is not a unique image. Therefore, this also is not a function. It has got 2 images. This has got 3 images. Right? Neither of the graphs given here represent functions. Vertical line test. If a vertical line cuts the graph at most at 1 point, it is a function. Maximum 1 point. Otherwise, it's not. In a function, every input from domain has a unique output from the codomain. That is why the second line. Now here vertical line test I have said here. See here. This is a function. Third one is a function. Is this graph a function? We will see here. This is not a function, because at this point output has got 2 outputs values. So f of x1 is equal to y1, y2 should not be. F of x1 should be only unique y1. Is this graph a function? We will see here. Yes, this is a function, because every input has got a unique output. Okay. F of x1 is equal to y1, therefore it is a function. Quiz. Which one is true? 1 to many is not a function at all. On to everyone is covered. Into some remains uncovered in codomain. On to everyone is covered. Right? This is the true one. 1 to many is not a function at all. 1 to many is not at all there. Right? And into all are covered here. Right? And many to 1 and on to everyone is covered. Right? So it is many to 1 and on to. On to because everyone is covered. And many to 1 because 2 input has got unique output, same. And here again, many to 1 and into. Into means 1 is not covered here. Some remains uncovered. So you know the difference between many to 1, on to and into. Into means some values in the codomain are not covered. All values are covered in the codomain means it is on to. 1 to many is not a function at all. Right? There is not 1 to many shown here. No. Many to 1 and into. Right? Because 5 and 6 has got 5 as the output. Into means some remains uncovered here. And 1 to 1 and into. 1 to 1 and into because something is not covered here. Right? One to many means not covered at all, not a function at all, but that is not shown here. Now we will see prime numbers. A number that can be divided by only itself and 1 without remainders, it's a prime number. 1 is not a prime number, because it is divisible only by 1. So not only one number, it should be divisible by 2 numbers. One by itself and another 1. It has no 2 positive factors, hence 1 is not a prime number. Prime numbers are 2, 3, 5, 7. I have written prime numbers up to 100. Actually within 100, right? Now we will see why is a number irrational. So numbers that cannot be represented as ratio of 2 integers. That is why it is irrational. Irrational numbers are real numbers that cannot be represented as rational numbers. I have given the definition. P is equal to x such that x is an element of real number minus q, rational numbers. P is equal to x such that x is an element of real number except the rational numbers q. Either way you can define. Pi is not a rational number. Pi is equal to 3.1419, non-repeating. Pi is close to 22 by 7, but 22 by 7 is a rational number. Pi is an irrational, so irrational is close to rational. Therefore, I consider an alphabet closer to q and r. R is a real number, q is a rational number. Therefore, p is close to q and r, p, q, r. Therefore, I will denote p as a irrational number. Properties of irrational numbers we will see. Rational and irrational numbers are alternate to each other, like I said, pi and 22 by 7. If a squared is divided by a prime number p, then a is also divisible by p. That means a squared, the factors should come in 2 pairs, no? Therefore, a squared should be a into a. That means prime number is a factor, means it should come as p into p. Therefore, p also should be dividing a. Addition, subtraction, multiplication, division we will see. Product of 2 irrationals may or may not be irrational. Closure property therefore fails. I'll take 2 irrational numbers, root 2 and root 2 is equal to 2. Therefore, it's a rational number. Closure property fails. I'll take sum of 2 irrationals. Sum of 2 irrationals may or may not be irrational. Again, closure property fails. 3 plus 2 root 2 plus minus 2 root 2 is equal to 3, a rational number. Square roots of any number that is not perfect square will be irrational. Right? 4 is a perfect square. Therefore, it is rational. But 4.23, root of 3, root of 5 are irrational. Properties of irrational numbers will continue. P plus q is equal to p. P into q except 0. Right? Rational numbers except 0 is equal to p. That is irrational numbers. LCM of q may or may not exist. Right? LCM of rational numbers may or may not exist. Addition and multiplication of p is not closed. Right? We have seen that. Irrational numbers have non-repeating, non-terminating decimal expansion. Irrational numbers 0.45678, root 3, and rational numbers are 5 by 11, 1 by 3. Please see here it is 4, 5 is repeated. Here 3 is repeated. So these are rational numbers. Then we will see set versus collection. Each set is a collection, but each collection is not a set. Only well-defined collection is a set. All beautiful women in India is not a set because we have not defined clearly what we mean by beauty. All 6 feet tall women in our family is a set. We have clearly defined who are all. Then we will see degree of infinity. There are different degrees of infinity, infinite number of them. Cardinality means what? Number of cardinality of PA is, power set of A is greater than that of A. So number of elements in P of A is greater than number of elements of A. That is what it means. PA means power set of A. For an infinite set, what happens to this rule? Do you say that more than infinity? Here comes a hierarchy of transfinite cardinal numbers. So you will see what then will be the opposite of that. The smallest of these is the cardinality of natural numbers. That is why we get a 0, right? In number of elements is 0 means in null element. So R is equal to x comma y such that y is equal to 2x, where x and y are elements of odd number, odd natural number. Now what do you mean by natural number itself is infinity? Then what is the power set will have? How many number of elements will have? Right? Is there a degree of infinity between the two? No. It keeps on going. Infinity is undefined. Degree of a polynomial, you will see. Degree of a polynomial is the highest of the degrees of the polynomials, monomials. Monomial means each term is a monomial there with non-zero coefficients. Right? Coefficient is not zero. Not zero means it has got a numerical value, real number. The individual terms in the polynomial are called monomials. That is what I said. Ax squared plus bx plus c is equal to 0, where a is not equal to 0 and a, b, c are elements of real number. Here the degree is 2 because x power 2 is the greatest power. Degree of a polynomial will continue. A polynomial consisting of one term, namely 0 only, is a zero polynomial. The degree of a zero polynomial is undefined because 0 is equal to 0 into any number, therefore undefined. A polynomial consisting of one term, namely non-zero constant only, is a constant polynomial. So any number constant 2, 3, 4 are all polynomials, constant polynomial. The degree of a constant polynomial is 0. But we will continue with the degree of polynomial. The limit of a polynomial function is equal to positive or negative infinity. It depends upon the leading term coefficient and degree, that is ax power n. A polynomial at infinity grows like the leading term containing the highest power of x. That is what the leading term I meant. If the limit is plus infinity, the function increases without end. If the limit is negative infinity, the function decreases without end. I think that completes the session on chapter 1.